All right, so this continues and builds on what we saw from the last lesson, which is still the first section of Chapter 5, which is representing patterns. And in general, if you have a relationship that's linear, which we saw last time means the change is constant, or if you graph it, it makes a straight line. But so far we're not really talking about graphs. But if we have a linear relationship, you can always express it in this form. Now, when you look at what you see here, it doesn't mean you have to have x and y, but in general, it's always in this form, where you have whatever x and y stand for. Maybe x is time and y is distance, to think back to the last set of notes. The coefficient of x, that is always your change, your constant change. In the last lesson, dealing with the odometer of a bicycle, that was 0.7, because every minute this person traveled 0.7 kilometers. And later on, especially in Math 10, we'll formalize this word constant change with the word slope. So I'll put that down now. But right now, that's it's kind of a lead into a word we'll use a lot in future courses. That's the coefficient. The constant term, the b, that's our starting point, or the initial value. Actually, I'll put starting value. And there's lots of phrases we could use for that. But again, thinking back to the last example from the notes, in which again we had the odometer on the bicycle, the starting value was 4.5. And so with that said, any linear relationship can be expressed in this form. That doesn't mean you have to have these variables, but it can be expressed like this, with you have some coefficient in front of one variable plus with a constant. And so again, let's look at an example here. A cell phone data plan has a fixed charge of $20 per month, plus $6 per gigabyte of data downloaded. So what do I want to do with this? Well, first, let's create a table where, again, I want D to represent data downloaded and C to represent the cost, the overall cost per month. So this table right now is empty, and I want to use this, though, then to eventually create an equation to represent this. And a key idea is that we can take any linear relationship and we can express it as a table and we can express it as an equation, and we can move between those. So, for example, for data downloaded for a table, let's just pick a number and pick easy numbers for ourselves and make a nice sequence. And I think the best number to start with is 0. What if you don't use any data? What if you just probably don't even use your phone? Well, you're still going to pay $20. So no matter what, there's a fixed charge of $20 per month. Okay, so what if I can pick any other number? The simplest, though, the simpler values I pick, the easier it is to see the pattern, which kind of makes sense. And so let's just pick 1, and then 2, and then 3. Now, in all reality, a person will probably use more than 0 or more than 1 gigabytes in a month. But let's just keep the numbers simple to see the pattern. So if you download 1 gigabyte of data in a month, you're going to pay $6 plus the 20, so $26. If you download 2 gigabytes, you're going to pay 2 times $6, so 12 plus the starting amount, so $32. If you download 3 gigabytes, it's going to be 3 times 6, which is 18, plus the 20, so $38, and so on. Now, for this table to be useful to me, it helps to have a nice, pick values that I can see the table, that you can see the pattern quite nicely. And having a 0 in here, the starting amount, is always quite helpful, because that's my starting value, as we can see right here. And so now from this table, I can see the pattern quite nicely. I can see, that it goes up by 6 every time, which again, I could also see from the writing of the question. However, I now have a table for this, and you may have already been able to determine an equation for the scenario before I made a table, but I want us to understand the connection between all these things. So if I want an equation that connects the cost for any amount of data downloaded, I can say the cost equals, and if I look at my equation up here, it can always be written in this form. So first, my coefficient. What's the constant change here? What's the change as we download more and more? That's a constant. Well, that's my plus 6. It's a constant. Every time I download 1 extra gigabyte, I pay an extra $6. It's constant. So one part of my equation would be 6 times, and I could put x, but why don't I put d for data? Okay, plus the starting value, which in this case is the 20, because no matter what, you're going to pay $20. And there's my equation. Now, if I just focus on all of this, we for sure could go straight from here to here. But one of the key ideas, and right now this could be something you're already finding quite straightforward, or it could be something you're finding quite challenging. The key idea is that we can take any, the idea is to be able to take a scenario and go between tables and equations in any sort of direction or any sort of order. All right, and so if I wanted to, I can now ask, well, what if you downloaded 10 gigabytes? You could easily just use this equation by replacing d with 10, and so on. So lastly, I want to focus on just some tables. And sometimes, depending on the values in the table, it can be quite readily apparent what the relationship is. Sometimes it's not. So I have 3 here. So for this first one, I have the variables x and y. Nice, conventional, boring values, but easy to see. First thing I would do is try to see the pattern. And notice, first of all, on x, I have nice, clean 0, 1, 2, 3. So as x goes up by 1, y goes down by 5. Every time we look down here, we're subtracting 5. So that's my constant change, minus 5. Once I know the constant change is minus 5, and I know the starting amount, because 0 is the start, or the initial amount, was 25, I can find my equation. And I can say y equals my change, negative 5, times x in this case, plus the starting amount, which in this case was 25. So my starting amount, my constant change. And I have the variables y and x, because those are the variables I see in my table. What would make this harder? One thing that would make this harder is if x, the table, was not going up by 1. The fact this was going up by 1 every time made it more straightforward. And the fact that we could see the starting amount. When x was 0, y was 25. If I didn't show you that line, we could still figure out this equation. It's still the same relationship, but it would be more challenging. So with that said, here's an example of one that's slightly more challenging. Same variables, x and y. I can see the starting amount, but notice now x is going up in 5s. Which means this is a different relationship. It's a different table. Right? If I look at this compared to the previous one, over here, when x is 3, y is 10. Here, when x is 15, y is 10. It's different. They're similar, but they are definitely different. So I should not get the same answer as before, because it's not the same relationship. But if I look at y, it seems to be this exact same pattern. Yes and no. It does go down by 5 every time, but that's when x goes up by 5. No offense to the number 5, but if I want to see this relationship in much more straightforward manner, I want to know what happens as x goes up by 1. So I need to proportionally think about this. Okay, yes, y goes down by 5 every time that x goes up by 5. But what about if x just went up by 1? How much would y go down by? Well, it would go down by 1, just proportionally. If we go up by 5 and this goes down by 5, then it makes sense if this goes up by 1, this will go down by 1. If this goes up by 2, this will go down by 2. I can now see that relationship. And so what's much more useful to me is what I just said, is that for every plus 1 to x, y, I'll just say minus 1 to y. Now that I see that, for every 1 that I add to x, I subtract 1 to y. Now I can see this change much more clearly, because this is my constant change, minusing 1 for every 1 increase to x. And so now I can say y equals my constant change, which is minus 1 times x, plus the starting amount, which was the same as before. And while this is great, I don't really need that 1 in front of the x. And so a little bit simpler is just to get rid of that. Y equals negative x plus 25. And if you're not sure, check. Pick a number for x that's on the table, for example, 15. And let's see, y equals negative, put the number 15 here, plus 25. And negative 15 plus 25 equals 10, which is what we see right there. So it's a good sign this must be correct. But notice that made it harder. I'd be very surprised if you don't find that at least a little bit harder than before. By the fact that in the previous one, x was going up by 1. Now x is going up by 5. That makes it more challenging, because if we want to figure out the change, we need to figure out the change for every 1 increase, not every 5. And so the last one doesn't have the starting amount, and it also doesn't go up by 1. Now, the fact we have variables n and a, that's not a big deal at all. So first, let's deal with the fact that I don't have my starting amount. That said, if I see the pattern here, this is going up by 10 every time. This is going up by 10 as this goes up by 2. OK, so I can see the pattern in one way. That's important. But next, let's figure out what happens when I have a 0 here. Which means, well, if I'm going this way, I want to subtract 2. Which means if I go this way, I want to subtract 10. Which means this must be 90. So there's my starting amount. When n is 0, a is 90. And what does n stand for? I don't know. Maybe number of something. A might be area, amount. Doesn't matter. I got my starting amount now. So I know part of my equation will have that 90. 90 will be the constant in my equation. But what's my change? What's the coefficient of n in this case? Well, again, yes, it goes up by 10 every time here, but that's when this goes up by 2. I want to think about what happens as it goes up by 1. Well, it's not a big proportional challenge. I can now see as n goes up by 1, that a must go up by 5. Right, just proportionally. Going up by 2, this goes up by 10. Well, 1 is half of 2, so 5 is half of 10. And so it's that change of 5 that really, really matters to me. And now I can see everything. I can see the starting amount, and I can see the change for every 1 increase at n. All right, so 5 is my constant change. And so I can say for my equation, a, whatever a means, is the constant change, 5 times n in this case, plus my starting amount, 90. And so notice again, by having my values in my table go up by a value that's not 1, and by having my starting amount not shown, it makes it more challenging. But once I find the starting amount and once I determine the amount it goes up by 1 every time, it becomes together quite nicely. Because whenever you find those two things, whenever you can find the starting value and the constant change, you can find your equation.